Okay, here we've got a trig subproblem, and unlike the others, this one has some endpoints on it. So let's go ahead and get started. We've got to we've got to complete the square here, and I think this one's going to be nice because x squared plus 2x plus blank plus 5 minus blank. If you take half the 2 and square it, you get 1. So the thing under the radical becomes x plus 1 squared plus 4. So this one's going to be a tangent. So this is u squared, this is a squared. So we're going to let x plus 1 equal 2 tan theta. So my dx is going to be 2 secant squared theta d theta. And my radical, it's the square root of this stuff, which we changed into this. So the square root of x plus 1 squared plus 4. X plus 1 is this. So that becomes 4 tan squared theta plus 4. So I can factor the 4 out. If I bring it outside, I get 2. And inside, I've got tan squared plus 1. Tan squared plus 1 is secant squared. Take the square root, you get 2 secant theta. So I'm going to put a box around all my substitution stuff. And now let's rewrite the integral. Let's see, dx becomes 2 secant squared theta d theta. And on the bottom, the radical turns into 2 secant theta. I'm not going to worry about my endpoints for the moment. I'm going to cancel stuff, and I'm left with the integral of secant theta d theta. And we know how to integrate that. It's from our formula sheet, it's natural log of secant theta plus tan theta. And then it would be plus c, but we've got endpoints on here. So let's go back and take care of those now. Now there are two different things we could do. We could either put it back in terms of x, and then use the original endpoints over here, the 2 and the 0. Or we could translate the endpoints. Normally I'm a fan of translating the endpoints. So let's start that and at least see what happens. For my upper endpoint, I'm going to take the 2 in, and I'm going to substitute into here. If I put the 2 in there, I'm going to get 3 equals 2 tan theta. That's going to give me tan theta equals 3 halves. Now that's not a nice number. If you take the arctan of theta, or if you take the arctan of 3 halves, you don't get something nice. If that had been arctan of 1, then we get pi over 4. Or if it had been arctan of root 2 over 2, something like that. There are a lot of numbers that would be nice here. But arctan of 3 halves, that's not a nice number. So let's don't do that. Instead, let's use a triangle to put this back in terms of x. All right, so I'm going to draw my triangle. Actually, before I do that, I'm going to put my endpoint. I'm going to put my bracket there to remind us that we have to put some endpoints on there. Let's see. Here's my triangle. Here's theta. Now, x plus 1 equals 2 tan theta. So that means tan theta is x plus 1 over 2. So that's the opposite over adjacent. That makes this side over here x squared plus 2x plus why did I put a 4 there? It's supposed to be a 2. It gives me x squared plus 2x plus 5, yeah. 1 squared plus 2 squared, yeah. Okay, so we get that. So tan theta we already know. Secant theta we can read off of here. Secant theta is, remember secant is hypotenuse over adjacent. So hypotenuse is this big thing. Adjacent is 2. So I've got ln of secant theta. Well, let's see, secant is x squared plus 2x plus 5 over 2. Plus tan x plus 1 over 2. And we're supposed to integrate this, or plug in 0 and 2 and see what we get. All right, well, let's plug in the 2. When you plug in the 2, let's see, what do we get here? We get 4 plus 4 is 8 plus 5 is 13. And then you get 3 plus 1, or 2 plus 1 is 3 over 2. Then when you plug in the 0, you get square root of 5 over 2. And then you get plus 1/2. And I guess we could leave it like that. We could also, well, we could drop all these absolute values because everything inside of there is positive. And then I guess we could also factor the 2 out. But I'm not going to do any of that. I'm just going to leave the answer like this.